I'm going to start with a quick few slides, just to explain what I'm going to talk about, what the aims of this tutorial is, what I'm not going to give. This is not an entire graduate level seminar or like a master's in statistics. Unfortunately, you cannot compress that into an hour and a half. I've tried. So firstly, who am I? I'm a senior data scientist at Channel 4. We're sponsoring. We're a media company, and we leverage data for targeted advertising, customer analytics, recommendation engines. We're hiring a junior role, so have a chat if you're interested. I'll be around here all weekend. What else do I do? So I'm an open source contributor to PyMC3. Those of you who do not know what PyMC3 is, it's good luck. Here we have a tutorial. It's going to involve a lot about it. It's a Bayesian Markov chain Monte Carlo framework. I have a mathematics statistics background, and I'm in too many different societies. I wrote a book, and it's not selling well, but at some point during the conference, I will harass you about that and make you buy it. Right, so statistics is everywhere. And I was at an event, a television event, a few weeks ago, and this came up, this survey. And it said, it was, of course, in numerous media outlets. And it says just 1% of men take shared parental leave. And of course, listening to Radio 4, I came across a question of what's wrong with this. Now, can anybody in the audience guess what was wrong with the survey? The survey actually looked at all men, regardless of whether or not they were likely to have children or not. So it took like a large population sample rather than people who were like to. And of course, this got rehashed, lies, damn lies in statistics, the famous quote from years ago in the Victorian era. But this got put around and used for political ends, right? That was the other thing. It could use to reinforce certain stereotypes and argue against shared parental leave. So for those of you who want to look into this, you can go to the BBC website, and they have the More or Less program run by Tim Harford, an excellent economist. And he talks about how the survey couldn't be sampled. It was actually using an off-the-shelf survey tool, and they hadn't thought about how the statistics was gathered and stuff like this. So that's kind of an argument to put it into context of as data scientists or data engineers, we generally will be using statistical tools, and we have to be very careful about what questions we ask and what these questions, what we can answer with our models or our samples or our hypothesis testing. It's very easy to just import SciPy and forget to think logically about what you're actually trying to solve. So hopefully by the end of this tutorial, you'll have a few tricks up your sleeve, and we're going to talk about mostly logistic regression, and we're going to talk about it in PyMC3, in Scikit-learn, and in Statsmodels. And this is the kind of question I wake up in the middle of the night and wonder about. And I'm not going to teach you all statistics in an hour and a half. You have to make these things clear at the very start of a talk. OK, so these are the outcomes of the tutorial. We're going to have 3 different tools to attack the same problem. I'm largely giving this tutorial because Ian convinced me to do it by saying, wouldn't it be great if you give a tutorial on this? And then before I know it, I had volunteered. We're going to have some tips and tricks like hypothesis testing and feature selection, but not too much about this. And we're going to talk a little bit about how to interpret and debug 3 versions of logistic regression: the machine learning way, in the scikit-learn paradigm, the frequentist statistics way, which you may know from school, and the Bayesian way, which you probably don't know from school unless you went to a very particular university. It's often not taught. And for those of you who are looking for the link, I set up a bit.ly link with PyData stats on it. So one thing I notice at conferences like this is that we do have a very much a machine learning focus. There's a huge amount of investment in academia into machine learning versus other ends of statistics. And there's this constant thing because of the big data paradigm and all these sort of memes that we're talking about. And we forget that there are tools that have developed over many, many years. Bayesian statistics go back to about 1850, roughly. And frequentist statistics, back to certainly the early 20th century. These have been refined, and they have a place in your toolbox. So I'm doing this under the assumption that most people in the audience are machine learning practitioners. Could I have a show of hands, anyone who identifies as a machine learning focused person? Okay. Anyone who identifies as a statistician? Okay, I'm definitely in trouble with you guys. Anyone who identifies as a Bayesian? Yes, great, there's one. We should definitely talk. But what are the rest of you guys? Like, randoms from the street? Like, surely, I know I've just invented 3 categories off the top of my head here, but are the rest of you just general engineers, academics? How many academics? Okay, so a lot of people really don't know what category they're in, but that's a different story. Okay, so Vincent, who's actually in the audience, I've stolen this from him, but I told him. But this is it's a nice diagram of the different schools of data, right? So you have your frequentist, you have your Bayesian, you have your machine learning. A lot of discussions will be around, at this event will be around here, things like support vector machines, how to deal with precision and recall, these sort of things. There'll be a few Bayesian talks, I think, because I think there's a few other people speaking this weekend. And I'm not so sure about frequentist talks here, but I welcome more of them if there aren't enough. So these are kind of the 3 different toolboxes. And the aim of this is if you know one of these 3, you'll be able to learn the other 1 or 2, and kind of use the one you know as a reference point for how you would approach the same problem in a different toolkit. Okay, so first thing I'm going to do hypothesis testing. And of course, those of you who are physics geeks will know that I took one of Einstein's hypotheses was recently proved, confirmed by empiricism in the LEGO experiment. And a lot of that was done on top of Python ecosystem, using IPython notebooks, and of course Stan, which is a domain-specific language for Bayesian statistics. So the sort of things that you support by attending conferences like this were used to confirm Genius German and his excellent work. So the other thing is that we're going to talk about we generally talk about normal linear regression. I'm only going to talk about logistic regression in this talk, and they're going to talk about these 3 schools: Scikit-learn, Statsmodels, and PyMC3. I'm giving you guys all time to get set up as well here. And you have Bayesian tooling, and there's most of the tutorial will be based on one of the pieces of documentation that is up online on the PyMC3 website. So now time to show some code. I've talked for long enough. So for those of you who have downloaded the code, there's a notebooks folder. In the notebooks folder, there's 2 files. One of the files is logistic regression. Can everyone see this? So it's fine for everyone. So the first file is logistic regression. As is always the case, we do our standard imports, for Scikit-learn. We import linear model, the train test split. I'm going to assume everyone in the audience knows what a train test split is. Otherwise, there are other talks during this weekend that you can go to. I used the data from the UCI, the University of California, Irvine. That's the adult data set. It's a survey from, I think, the 1950s about how much people are earning and what they're working in, stuff like this. It's just a nice data set. You could pick any other one. So the first thing that we do, of course, is we have to remove all the nulls in income. So you don't want to, if you want to predict something on income, you don't want to be predicting on nulls. I say this because even after a few years of doing machine learning, I still run into this mistake of forgetting to deal with nulls in the column. We're restricting only to the United States for reasons of easiness. I'm glad you're in the front row.
It is a very easy place to start with.
And of course, we're all trying to download the data from the UCI website. I hope this survives this tutorial as well, because that would be quite embarrassing. Okay, is everyone who wants to following along? Does anyone need another couple of minutes? I'm fine to give you another couple of minutes. I can talk very fast.
I want to follow along.
Do you want to follow? You don't want to follow along? Oh, thank you, James. Yeah, it's great to be heckled here, and it's this early in the morning. Sorry? Sorry, I can't hear you. It's in the Slack channel. Here, if I show this again. There, bit.ly/PyData LDN stats2. That should get you to my repository. Okay? No problem. Here to help. So the first thing we do is, of course, we have to create a binary variable, which is very easy. I pick greater than 50K for reasons of randomness. You can pick whatever you want. This is just a classical use case of using logistic regression. This could be a churn model. This could be whatever else you want to work on. The other thing I do, which is a standard trick, is to square your age variable, assuming that you have some relationship. Basing this on some other work I did, like analyzing the data set before. But this is the kind of standard trick you would do with a numeric variable like this, assuming that you have like a nonlinear relationship between this and the thing you're trying to predict. Some of this you can do randomly, some of this you can do systematically, some of this you do out of habit. So we restrict the data set to stuff that we could actually use. We look at the income. We've got class and balance here. It's actually quite difficult to see, but here you have a lot more zeros than ones, right? So you're trying to predict on a class and balance data set. Reason I picked this is that this is a very classical problem. Real life is generally not a balanced thing to predict on. If you use good practice, you do lots of plots. If you don't use good practice, you should do lots of plots. And C board mix is very easy, and you can have an idea of what data set you're dealing with. This is just like as an approach, a standard best practice approach for predicting things. So because you have in Scikit-learn, you have a logistic regression, you have a few parameters. The first one here, I've just changed the constant to something very high. I'm just doing this to have a feel for and this is probably also my generic first logistic regression that I apply to any problem. We can ignore those errors because I don't have time to deal with this. But, and in the machine learning paradigm, we have scores, right? So we have scores of accuracy. So the first thing we do is we look at the score of our accuracy on the training set. So that's about 80%, which is not great. It's not amazing. It's not anything you use in a fraud detection problem, not unless you want to lose lots of money. But it's good enough for a lot of problems. And then you compare it to your kind of your worst case scenario, the dummy variable. So we have decent predictions, but not great ones. Only 24% of the class earns more than 50K, which means that you could obtain 76% accuracy by always predicting no. So we're doing slightly better than the null error rate, but not much. So the next thing you kind of do is you'll evaluate your coefficients. So this is a standard approach that you have in a machine learning problem. You're looking at your coefficients, you're looking at how they're related with the thing you're trying to predict, you're seeing if there's any insights you can get out of there. So that's kind of like your standard workflow. The one thing I haven't done so far is I haven't really split things into a training set and a test set. But nobody corrected me on that, which is clearly indicated that it's far too early in the morning. So I have a slightly different model, which is the class, the normal, the default settings. And then I want to predict things like my class model, Oh, I've done that too quick. And then I want to do things like generate my probabilities, just to show some of the functionality in Scikit-learn. So we can look at this model as a black box. I'm obviously not going to talk too much about machine learning, because my whole agenda with the talk was to talk about PyMC3, but big surprise. But this is the kind of standard workflow you'd have. We're all familiar with this. This is what we do. Some of you in the audience are going, I should plot more often, which yes, you should. And there is a good, robust paradigm here that you can use to score and understand a problem. But this is very much a computer science centric way of looking at the world, right? There's no uncertainties here. We don't have any notion of our uncertainty in the thing we're modeling. We have like a black box kind of thing that we're accepting, will work. Now it does work because some of us make a lot of money and some companies make a lot of money out of using machine learning. I'm not arguing that we should abandon machine learning, but I'm saying that for some problems, particularly ones that you want to interpret and understand the phenomena, there are other tools, mostly from the world of statistics. So, is everyone following along? Am I talking too fast? Do you understand my accent? All these sort of questions.
Sorry, just one quick question.
Go on.
So you said this is an unbalanced data set.
Yeah, it's a class imbalance data set,
So
yeah.
typically, what would you do? Just use the weights to try and
Yeah.
the imbalance?
Yeah.
Anything else in there?
Yeah, you can also do things like you can, I wish I'd put more stuff in model debugging, but I didn't have time. There should be talks over this weekend on that. We can definitely have a chat about the different ways that you can look at that. You can look at the individual things and plot using like a heat map or something to see if where in particular you're misclassifying things. And then you can also do things like hyperparameter tuning, which is something which I didn't have time to go into, like to actually find the optimum parameters for that problem. That's kind of the only ways I can think of off the top of my head. You can normalize your balance sets as well. That's one way of approaching it. But this is kind of an entire phenomena as well, like an entire era of modern day machine learning research of because of things like fraud detection problems and stuff like this. If you can find anybody who works for a fraud detection company, which there are probably definitely people in this room and definitely people at this conference, they may be able to tell you even more tricks that they have up their sleeve for dealing with that. I hope that's a good enough answer.
Good, thank you.
Okay, so I'm really not going to run through all this code here live because I know this will be a good way for something to break. And the things you learn giving talks, never do live demos. So if you open up the document, the other one, the statistics, this is where the real meat of my talk is. The first thing I'm going to talk about is a bit heavy and difficult. I do this because it's early in the morning. I want to wake everybody up. But it's Bayesian A/B testing. It's from Maciek Kula, who's at List. It's on his blog, on the List blog. It's a standard use case of where he simulates the results of an A/B test by assuming like a beta binomial distribution, which is a fairly representative distribution for what will happen in an A/B test, because most people, people do not follow a Gaussian distribution. You have these kind of different distributions out there. And he uses that to generate sample data from an experiment. And he has things like your treatment and your observed outcome. Then the other thing he does, and this is, for those of you who've never used PyMC3, in PyMC3, you always have this with model syntax. This is a context manager. Within this, you specify your parameters. So here, on the blog, there's an entire equation of what you would do it. I didn't want to put too many equations because I didn't want to scare everybody out of the room. It happens. And this is your prior sigma, your treatment sigma. The control mean is something that's a distribution that he's already specified. The treatment effect is the thing that we want to find, which is the difference in means, right? So the difference between your control mean and your treatment mean. This is a thing that you're really trying to get out of your A/B test. This could be, for example, a conversion rate, right? Because most of the time with these kind of tests, you're looking for the difference in two statistics to see if something is actually reasonable or not, or something is statistically significant. And then there's kind of this other stuff that you have to do to get this stuff into a model. The other thing that you have is you have outcome, and your outcome here is the thing that you're actually going to simulate. This is really your likelihood. Here in PyMC3, you have to specify your number of samples. You have to use something called the maximum a posteriori algorithm. This is to find the starting point, because it's very important about where you start this simulation. I use Metropolis, which is a standard algorithm. And then you just get your your trace. I had to discard some of the burn-in because the first part of the simulation didn't converge very well. And then you can output this all into a data frame. So this might be a bit heavy for you right now, but we will learn more about this. We will whenever we go through the logistic regression stuff later. I just didn't really know where to put this in the talk. So you can generate your data, then you can fit your priors, and then you have your treatment mean. And one of the things you're going to observe is that the treatment effect, which is a thing that we're trying to look for, this is our effect, has as a minimum value negative, which makes no sense in this kind of test. You would not expect to have a negative effect. So clearly, this here model is crap. We should never use this. But this is the kind of thing that you'll notice whenever you're debugging these kind of models. It's very easy. And in his blog piece, he goes through the need to specify priors in a more clever way and how constantly looking at output can evaluate. This is just a way to show you of the kind of failures and risks that you have whenever you apply this approach. And hopefully, before the end of the talk, we'll talk a little bit more about how you debug these models. I just wanted to show you something rubbish first, and then try to gradually show you better stuff. So if you want to play around, you can just run through that model and change one of your priors, and then run it again and see what happens. But because there's a large audience and it's quite difficult to keep everybody's attention, you might not want to do that. But I'll give you a couple of minutes if you want. Does anyone have any questions right now? I know that's a bit heavy right now, and that was just to show you as a proper use case. We're going to go through this stuff in a bit more slower detail now. We're going to look at hypothesis testing first in frequentist statistics, using mostly SciPy, and then we're going to look at hypothesis testing in PyMC3, and then we're going to look at machine learning, frequentist statistics, and PyMC3 for logistic regression. Yeah, I love when people ask me that question. So there are rules of thumb is one thing, particularly from biostatistics and experimental work. There are also studies about there's things there's something called a Jeffrey prior, which I forget what it is off the top of my head, but there are ways of picking that. But unfortunately, every time I look into the literature, I do discover this kind of there's a subjective aspect of that, and I don't think there are algorithms in the same way that there are hyperparameter picking algorithms in machine learning, that you can find the optimum hyperparameters for your problem in Bayesian statistics. But that's kind of a research area that I'm not an expert on, and the way I was taught it was that as your domain knowledge gets better of a phenomenon, you just get better at picking your priors. But there is also the converse thing, which is that by picking uniform priors or non-informative priors, this is what's going to happen if I talk too long. Is that back? Yeah, it's okay. That's fine. Then as you get more data for a problem, that becomes less and less important. So you get that kind of Peter Norvig said, the more data becomes more important than algorithms in a certain class of problems. So that does seem to be true in the Bayesian context as well. I hope that's a satisfactory answer and I haven't completely fibbed you off. Okay. So we're all going to go back to school, and isn't that a terrifying prospect? We're going to talk about hypothesis testing, right? So this example is shamelessly stolen from Chris Albin. This is roughly speaking what an A/B test is, right? You have an A, you have a B. You want to see if they are there's a statistical significance in their difference. So the first thing you do is we're going to generate a random X, which is uniformly distributed. And of course, I haven't imported NumPy. Seriously, nobody do live demos. They're a really bad idea. Right, okay, that's fine. So you have this, and you can see this is a uniform distribution. In the same way that if you're picking a uniform prior, in a Bayesian context, it would look roughly like this. Right, and the other thing we're going to do is we're going to pick another distribution which is definitely not uniformly distributed. You can definitely tell this is not a uniform distribution. I have no idea what this distribution would be called. I'm sure someone named it. The first thing you're going to do is in SciPy, there are loads of statistical tests. I'm going to say something which is controversial, which is that you should just probably use Kolmogorov-Smirnov because it's a pretty good test. Whichever one you like, use it. Whichever one you don't like, don't use it. They have their strengths and weaknesses. I don't have time to go into all the details. There are statistics textbooks you can get in Waterstones or Amazon or whatever. Or talk to me over the weekend. And from this, you can see that we want the second return value to not be statistically significant, meaning that they both came from the same distribution. So we've confirmed that X, our first distribution, is a uniform distribution. So as an exercise, I want you to change that line, the uniform, to something else. You can put normal. I need to look at the documentation to know what the distributions are there, but binomial, whatever, and compare it. That's the kind of thing you can do just to get used to using this if you've never used SciPy for a statistical test before. So the reason we use it is as non-parametric, so it doesn't have any of these assumptions built into it. One of the things you will discover as you look at these statistical techniques is, although the algorithms are very easy to use, and it's roughly speaking one line of code, there's a lot of assumptions baked into how they're used and how they're not used. And so for the second one, we can see that the p-value is less than 0.5. And there we can say that the y is definitely not a uniform distribution. If you do A/B testing professionally or you work in pharmaceuticals, you spend a lot of time doing examples like this. And that sounds like really lots of fun. The other thing you can use is one of the standard t-tests. But this is a frequentist way. So I'm Bayesian, and I don't care about frequentism. So but I was showing this as an example. These are the kind of standard tests that you would do to better understand, the results of an A/B test, a classical example in e-commerce. Is there a Bayesian way to do this? There is an algorithm or a method called Bayesian estimation supersedes the t-test, which clearly has the best acronym ever, BEST. This is from Thomas Vecchi's example. It's based on a paper by John Crooks. I think that's how you pronounce his name. He wrote a book, a Bayesian book that I forget the title of, that has dogs on the column on the front cover. It was a really good introduction to Bayesian stuff. Not just because there's dogs on the front cover, but that is one of the reasons I pick it. And in this, you will see. We're going to do the same model. You can see this is also a lot more involved, right? So in the previous example, I had one line of code. Now I have lots and lots of lines of code of setting up my priors and setting up my likelihood and all these sort of things. And that's a little bit irritating, but we could probably fix that. So if anyone wants to be daring enough to run that and see if it actually works, I'd love to hear. So that's running, and that will take like minutes and minutes. Does anyone have any questions right now? Like where we are, everyone's following roughly, kind of understanding what I'm talking about. No one has any installation difficulties. That's amazing. Actually, no one's actually. That's never happened before. So you can see so now it's greater than 50% through. It's going to be about 30 seconds to run this whole thing. Unless I think that will be it. And in the PyMC3 stuff, we have you can look at your traces. Now, does anyone see anything wrong with this model on the right? You'll see here that, like, for these different parameters, these different models I'm trying to simulate, the convergence isn't very good, right? So this should be, like, entirely smooth, rather than like stopping about here. So this model is far from perfect. And this is one of the things that you'll look at if you want to build Bayesian models about, like, the good performance. You'll look for, like, and in the documentation you'll find examples that are actually good. You will see, like, lots of examples of good convergence. The ways to do that are you either pick a better starting point in the space that you're trying to simulate. That's unfortunately something that we learn from experience. Or by picking different sampling algorithms, some of them perform better in different cases. I'm sure there's literature out there about why you would pick it, and there are definitely people here at the weekend who know more about this than I do, who could probably tell you about why you would pick that versus other things. Could also be bugs in the code, in which case it's probably my fault. So then the other thing you'd want to do is that after you've looked at, it's in my code here, it's from John Cedar, who I think is speaking this weekend as well. He added some nice diagrams to the code, so to the plots, so you could better see where the mean was and stuff like that. And of course, I didn't import that properly. So at some point, I'm going to learn not to try to do live demos, but that probably won't happen today. So so then it's slightly better, and you can see more things here about, particularly where the mean is on your frequency and your difference of standard deviations. So then the other thing you want to do is, like, because for these kind of problems, you want to look at things like autocorrelation, which isn't too bad for this model, if I remember correctly. So it's quite good for everything except nu minus 1. And there's other models I think I have in the notebooks here that are even worse than this. That's the kind of thing you want. You want this to go down to 0 as quickly as possible. That's kind of your good rule of thumb for this interpretation. Okay. So you can do, so these are the kind of things you'll need to debug models in a Bayesian context. We'll move on for this now, but we should be aware the model isn't perfectly, go on.
Does the correlation Bayesian setup affect the model in the same way as in the frequentist estimation?
Pretty much, yeah. It's, I think they're theoretically equivalent. So, like, in the same way in time series, if you're doing a time series model, you would look at your autocorrelations to see if that would tell you, anything about, like, that you've got interactions there. It's pretty much the same. And there's probably some professor somewhere who would disagree with my statement there, but you'll probably find a professor who will disagree with any statement I make here. So, okay. So now we're moving on to the meat of the talk. I think I've got like an hour left, so I might finish ahead of time. Like earlier on, we download our data store. I'm going to do that again. We're going to apply Bayesian frequentist and machine learning approaches to this data set. The problem is going to be predicting income greater than 50K, which we showed earlier on in the machine learning example. Is anyone still following along? That's amazing. And this will take some time. So I'll just wait for that to download. So there's a whole load of data here. It's got categorical variables and stuff. I basically just took everything that was numeric, and ignored all the categorical stuff. This is not good practice, but this is a tutorial, and so what do you expect? And then you want to restrict these things, the same as we did earlier on. So we want to talk a little bit more about doing our feature engineering. So you look at our head, do the same thing as earlier, make income into a binary variable, have your age squared, and look at your class and balance data set. So one of the things, because the first thing I'm going to do is the machine learning example. One of the things you can do using in Scikit-learn is you can look at how your features are, how much mutual information there is in your features. And this is, and I only discovered this like last night at 11 o'clock whenever I was writing this talk. But yeah, it's actually quite cool. Like, so there's these kind of metrics that are in there, in Scikit-learn. And you can use them to see if because one thing you don't want to happen in this model is you don't want redundant features, or redundant covariates, depending on which side of the fence you're in. So this is one way that you can look at. It's in Scikit-learn. It's very easy to write. You can probably copy and paste this and use this forever. And you can see that the scores aren't very good, which indicates if they were closer to 1, there would be more stronger correlation between these variables, and therefore you could probably get rid of one of those features. There's many other feature selection algorithms in Scikit-learn. You can use them. If you're building a Bayesian model, what I often do myself is I will use the Scikit-learn stuff to understand what my feature set is like and use that to form what kind of logistic regression or linear regression model I build in a Bayesian context. So you can always you don't have to pick a side. You can use the tools from the different sides that are out there, and this works quite well. So the other thing, like we did earlier on, is that we want to explore our data. We want to look at our correlation between our different variables. And we want to do a machine learning model and be boring again. And I used exactly the same as the one I did earlier on. And we scored. We have our accuracy. We have 79%, exactly the same as earlier on. Everybody's very happy. So believe it or not, in Python, there's something called Statsmodels. It's this horrendously neglected project that is aiming to bring statistics to Pythonistas. If you're willing to contribute to open source software, please contribute to that one, particularly if you have expertise, but that's generally not a barrier to entry. And this is, because there's lots of things like it needs documentation, it's got like a release coming through, but it's actually got a lot of good stuff there. A lot of people think that you have to move to R or something else, or Julia, whatever is cool these days, and to do statistics. But we have logistic regression, good frequentist logistic regression, in Statsmodels with good summary tables. It can be used. People use it in production, so that's a good sign, unlike Julia. But I knew Malcolm was it. And then the first thing is to use list comprehension to get our training columns. do it. Oh, this is something that I do find annoying about stats models, is that you have to do things back to front, right? So in Scikit-learn, you would do the X here and the Y here. Here, you have to do it the other way around. The reason I'm saying this is I have spent hours and hours, like a retard, not really understanding what's happening, and then realizing in the documentation that because of the way they think about statistical problems, you have to do it the other way around. So these are the kind of things that we all deal with on a day-to-day basis, and I wish they were more well documented. And I think the only way to learn those things is either bang your head against a wall or come to a tutorial with me. So then you get this fit, current function value. And you have your results summary. So there's a lot of detail in the results summary. One thing I had to learn whenever I was writing this is that there's something called a pseudo R-squared value. The reason is that for logistic regression, you can't just apply an R-squared value in a classical context. You have to apply a hybrid, a different version called a pseudo R-squared. The same kind of rules apply. It has rules of thumb. In fact, in stats models, it's a McFadden's pseudo R-squared value. There are other pseudo R-squared values. As you can tell, I really enjoy reading this stuff. And I've written it in the code for a reason to have this included. The take-home point for this, though, is that the rule of thumb is that if it's between 0.2 and 0.4, then it's a good model, right? So that you have a good model fit. This one's a bit below this. It's 0.009, so it's actually not a good model. I think I wrote not so bad. I was clearly feeling more optimistic when I wrote this. But this is the kind of thing you would have, right? So you have these tools to evaluate your model performance in the same way you would evaluate a machine learning model's performance. And they're all built in there. And if you want them to improve, you can submit a pull request. Okay, so in PyMC3, there's something that's actually very well written and easy to use. And that's like the linear model syntax. So you'll see here that you have your income proportional to your age plus age squared plus education plus hours, your data log. It's a binomial model in this case. You have your samples. For those of you who do not know, this is called a no U-turn sampler. It's one of the next generation of Markov chain Monte Carlo methods. It's one of the really great selling points of PyMC3 because I think it's only Stan that actually has this implemented other than PyMC3. It's not in PyMC2, for example, and it's not in some of the other frameworks that are out there. I'm not going to run this because this model took me 535 seconds. So just so you know, if you're about to run that, I'm sorry. So it could take, this is clearly one reason why you would not use a Bayesian model for online learning, because you just have customers waiting there forever. But it can be very good for problems that you're not going directly into production, depending on your definition and time scale of production. So those of you who come from an OR background, this is very similar. Those of you who use Patsy, this is very similar. It just makes it really easy to use. So now particularly in logistic regression models, Bayesian logistic regression models, we're getting very close to a Scikit-learn kind of easy to use, numbers and lines of code, easy to edit, stuff like this. This is not as complicated as the first one I showed you earlier on, which everything had to be specified individually. So this is kind of I'm just showing this that for people who think PyMC3 is hard, it's clearly not. Look, I wrote it. But this stuff is here. It's very easy to use. It's a nice little alternative thing if you've just done a frequentist one. You may want to start to do Bayesian and frequentist ones all the time. You may not. That's your choice. And I'm not going to run this because it's going to take forever, even though I do kind of have time. Oh yeah, right. So if you look at the autocorrelation plot for this one, you can clearly see this is rubbish, right? So age, for some reason, has not converged at all. I don't know what's happened here. The last one kind of worked. This is clearly like, so a naive model that, the first thing I would do, clearly isn't going to be perfect. So then the other thing you can do is pick, better sampler or a better starting point, or let it run for a longer period of time. Maybe 600 seconds isn't long enough for it to converge. These are all entirely possible. These are just things you learn whenever you diagnose. The reason I'm showing something that's crap is that this will empower you to do something that's better, and that's kind of like the best you can do sometimes. So now that you've done this computational effort and you've run these like Markov chain Monte Carlo methods, one thing you'd like to do is to actually take advantage of the real strength of a Bayesian approach, right? So one of the real strengths of a Bayesian approach is that you always have baked in things to do with uncertainty. So in the previous example, you'll notice of the frequentist approach, you just have a value. You just have like a pseudo or squared value or an AIC or whatever your model performance metric is. That's just a number. You don't have any clarification of like the degrees of error of that model. You don't have any notion of how uncertain your modeling approach is. And this is one of the real strengths. Of course, I'm a Bayesian fanboy, so I strongly believe this. But there's one of the real strengths of a Bayesian approach. So we're going to look a little bit at some of the tools that are out there, like for like evaluating your model performance. So I'm not going to run this because I haven't run everything above it, but you can look at what your distribution is of your different beta things that are coming out of your model. So if you look at this one, this is one of the plots I made earlier on. You have your posterior predictive distribution, right? So this is kind of your way of evaluating your approach to a model. And you'll notice in it that your probability of having an income greater than 50K in this data set is almost 1 if you're like 50 years old and you went to grad school. So you can see you can look at your entire distribution here. You can look at how your age changes. You're getting a lot more information out of this modeling approach. Now remember, it was roughly the same number of lines of code as the frequentist approach or the Scikit-learn approach. Rather than getting things like precision and recall, which are the classical things in the machine learning paradigm, you're getting a good understanding of what's actually happening here in your different in the different variables that you have out there. And the variable here is high school education, bachelor's education, and grad school. And this also goes in accordance with our intuition. You would expect people who went to grad school to have a greater chance of earning a higher salary than those who don't. But you can see also these kind of tipping points that you get with a lot of these phenomena. Is everyone following? I haven't bored anyone yet. Well, some people have left, but we'll ignore that. No questions? So, just like in the frequentist approach, we have this kind of your odds ratio. And this tells you your probability that something, hold on, how do I explain this? It's a model performance metric for telling you how likely an event is to happen. But generally, whenever you write this in a frequentist way, you only get a number rather than like an entire distribution with your credibility interval. And the last thing, and I'm realizing I'm definitely finished ahead of time, so there's plenty of time for questions, is earlier on, we picked age squared, right? So you pick the age squared on our model. Now, the reason we did that was voodoo, and like I just pulled it out of I don't know where. But there are actually ways in the Bayesian context called, there are model performance metrics, and one of them in PyMC3, which I think I might have contributed, is the deviance information criterion. So in the frequentist context, you would have something like an alkyd information criterion, which you also have in Scikit-learn, as a way of picking your model, right? There are these tools in a Bayesian context. They're in PyMC3. You can use them. I wanted to show them as a. So here, this little model thing that I've run has K1 all the way up to 4. So what I've done is I've multiplied age by this exponent. So the first one's age 1, second one's age squared, third one's age third, age cubed, age 4. And then whenever you run it, you see that you don't get a lot more information. Like you'd a lot more information by going up. They're all roughly the same. So it's reasonable to take just your age squared as your extra variable. You could pick one of the other ones, but you don't get a huge increase in extra model predictive power, to use like inverted commas, by going up on that. This is the kind of thing that you use to evaluate if you've made the right choice, and this is in the documentation as well of how you would choose a different, which exponents you use in your model. Because sometimes you might not have domain-specific knowledge, and you might want to use a model, like a framework or a metric, to help you target that in your modeling. So guys, that's actually all I have. So I've completely mistimed this completely. For that, I don't know if I'm sorry or if you guys are just lucky. Does anyone have any questions? Was that too fast? Do you want me to go back over anything? I do have time still left. Or is everybody completely satisfied and they just want coffee? Sorry, go on.
You mentioned a few problems with the models. We saw like autocorrelation and convergence problems. So maybe you could tell us about the starting points where what you would try to do first to improve.
Well, the first thing I would do is I would run like your MAP to get a better one. What you can do within that is you can pick a different solver, right? So often, and these are just the optimizer. So it's an optimization problem. You're trying to compute your best starting point, and what you can use in PyMC3 is you can use any of the SciPy solvers. So like there's F-min Powell, there's LGFS. If you read the documentation, you'll see that like some of them have better strengths and weaknesses. I think for because there are various points, like you'll see this in the documentation as well, but there's various points whenever I've been building models when just simply changing the solver had like a huge increase in the convergence. And there's clearly, I haven't always had time to go off and investigate the really viable theoretical reasons for that. But often it is just because of how they solve a problem. And it can be stuff like to use the physics terminology, your phase space could have like a singularity in it. And then there are some solvers that are just much better at dealing with that. Because some of the solvers add like a certain degree of randomness and they'll jump to another point and then they'll find a better starting point for you. So that would be one approach that you could have to that sort of problem. The other thing is to just try some of the different algorithms there are for sampling. They will have different strengths and weaknesses. Sometimes you could know from, if you have deep domain knowledge about where these things are, about where to put your starting point, you can specify it yourself. I think that's really all you have, as a toolkit that I can think off the top of my head. I hope that was a decent answer for you.
Yeah.
Oh. Anybody else? Yeah.
I have a simple question.
Go on.
So PyMC3 depends Cyano.
Yes.
So does that mean you need a C compiler to use PyMC?
Does that mean you need a C compiler
To use, not to install.
to use?
Because I'm not so familiar with Cyano.
So, that's a
That's okay.
that I think you do. I think in particular. So, if you're I think if you're going to be running it on Windows or a certain architecture, you probably have a bit of work to do that we haven't done actually. In terms of Theano, I think Theano you can ship in a wheel or something like that. That was probably one way to include all the C extensions you need. Because Theano compiles to C, but it should use a C compiler of some description, and I don't know which one it is. Does that answer your question? Why did you ask that specifically?
Well, it's like how is it to use for people?
Like, well, I installed it on this Mac, and I've installed it on Linux, and that's all you really need to use, right? Almost. I've not had any huge installation problems with Theano. I have had problems with Theano. Theano is very complicated, right? So it's written in a very functional style. You can't actually do for loops in Theano, which is surprisingly annoying. You have to use like this scan object. So like and Theano is also undergoing a lot of development in Montreal. So like the biggest problems we've had with Theano have been that it's changing, and it's complicated.
Yeah, and that was my next question. Is
Yeah.
how stable is PyMC3 in terms of API?
Well, the API that.
Yet, right?
Sorry?
It's not released yet, just to show.
We're beta? Does that count as release? I don't know. Does anything count as release these days? How stable is PyMC3? The API is not going to change a lot. That's been kind of like built into the design pattern, by likes of Chris Fonesbeck and Thomas Vecchi. So that, unless they change their mind, that's another thing that I'd have to know about. I think the real thing PyMC3 just needs to be done for it to be at the release stage is lots and lots of documentation, which I keep meaning to write, and never do. I might do a sprint at this event, and that might be one way. So that's one thing. The other thing is like there were a few bugs in the samplers, but that hasn't changed the API, right? So the sampler, like there's been a few bugs in that. There was a few bugs fixed recently in the non-U-turn sampler, but that was only by people exposing it to different new edge cases, right? So.
I was most concerned about the stability. Like, is it something I can advise to some customers to use or not? Like,
don't know if I want to publicly say yes to that question, but I hope so. Is probably my answer. Quantopian are using it. Thomas is using a Quantopian.
do they expose it? Can you use it directly from? I've never used a service.
I don't think they expose it directly, but I think in some of the stuff that you get from them, it's used in it. Any other questions? That's a lot better than I normally do. Normally I take too much time. This time I thought, yep.
I have a more general question about
Go on.
using Bayesian methods in production. So maybe you could give an
Define production. Define production.
Well, for example, you mentioned that something like online, real-time analytics.
I wouldn't use it for that because the time to compute is just a hard problem. You can infer from, if you read, Cameron Davis and Pylon wrote the book Probabilistic Programming and Bayesian Methods for Hackers. It's written about PyMC2. There's a project to port all that code to PyMC3, which I'm looking for volunteers for, by the way. And in it, he talks about this problem, right? So he runs a model for, what is it? I think it's like a bandit problem, like an A/B testing like thing, and then he takes an approximation of that model and uses that as the thing you would expose. So he uses like, an approximation for what the model results would be, which is just something that you can compute by arithmetic. So I wouldn't recommend like exposing a Bayesian model via a RESTful API as something on a day-to-day basis. But most analytics does not need to be like that. So I would argue that although like it doesn't do great in real time and online, for a lot of problems, particularly something that's an internal tool or something that is actually like analytical, like type A focused data science, Bayesian approach certainly has a lot of strength. Is that a good enough answer to you?
Yeah.
Okay. Go on.
Maybe
Go on.
allow me to comment on this.
Please do.
There are some Bayesian techniques you can use for like online computing, but I don't know if PyMC is a good way. But like I think like a Bayesian particle filtering,
Yeah.
this kind of techniques you can use for online.
Yeah,
I
yeah.
mean, I don't know if it's easy. I don't know any of package that you can use in production from Python. But
Yeah, yeah, yeah. Yeah,
that's
but
something you can look at if you're interested. So Bayesian particle filtering.
yeah. There's definitely something that's on my reading list as well. So
What was that, sorry?
Bayesian particle filtering is what David just mentioned. That's, sorry? I'm not going to explain that because I know nothing about that. I know it exists and I know the terms, but like I have no expertise in that whatsoever. I know people have been using it for online learning, but that's all I know. I'm sorry, I don't know everything.
It's like fancy Kalman filtering. If you're familiar with.
Sorry? It's like,
fancy Kalman filtering.
yeah, yeah. Yeah, so if you're using, like, if you had time series stream, you might use it as a way to do inference on that. It does strike me as a bit too complicated, like, and Kalman filtering's a lot more well established and the algorithms are there. Yeah. Any other questions? Yeah, yes?
So would the Bayesian approach to feature selection be much the same as traditional methods, or is there anything?
The Bayesian approach to feature select. Yeah, well, see, the sort of results I showed, like, of your features, you could use them, and people do. You could use them, like, to inform your feature selection, like, for a machine learning model. So, yeah, I've heard people using that in the past, and that is, like, they use that to get extra information about the features that they wouldn't get from another approach, and then, like, put it into a machine learning model that they could expose by an API. That's a pretty good approach. It's using different tools, but yeah. So I see a lot of the Bayesian stuff as like very much a R&D, as opposed to like a type B data science, like engineering and putting it into a service, because of the nature of the beast. Okay, is that a good enough answer? Yeah. Okay. Any other questions? Go on. What's my book? My book's called Interviews with Data Scientists. That's exactly what it is. It consists of 24 interviews with people from Shopify, Cameron Davis Python's in there, Etsy, Amazon. I think there's someone from Facebook, but don't quote me on that. And there's people from all over the place. Eric Bernardson, the creator of Luigi, who was at Spotify, he's interviewed in it. Hadley Wickham's in it. And Ian Oswald, who runs this conference, is in it as well. So for that reason, you should definitely buy it. I'll put it up on the Slack channel later on. Any other questions? Right, so I think that's it. Oh no, go on.
So, for example, if we are talking about simple Bayesian model like linear regression,
Yeah.
How easy would it be to distribute it?
Distribute it.
Yeah. Impossible or worth trying?
I've learned not to say things are impossible. Generally because someone then disproves me and I look like an idiot. So you can definitely distribute the Monte Carlo part because that's an embarrassingly parallel problem. why would, I don't know if you'd want to, but that's a different story. But then the other things, like the kind of like getting all that information back, I'm not so sure. That's the part that I have trouble with. So distributed, not out of core, right? You're not talking about out of core.
No.
Right. So I think there are methods for like out of core to use like multiple CPUs like in one computer. I'm not familiar with anything distributed like that. It wouldn't surprise me if someone's tried it. I'm sure someone is doing it. Yeah, I hope that's all my knowledge of that. There's definitely people have talked about it. And it's online somewhere. There's discussion, probably in PyMC3 as well. But I'm not an expert on that sort of stuff. I try to avoid distributed computing because it causes me problems. But that's my own prejudice. Any other questions? Yep.
So in practice, do you usually use sampling methods, or most of the time it's enough to just pick conjugate priors and that's it, and just bypass?
Most of the time, I probably pick uniform priors or flat priors, to be honest, which is probably not a Bayesian approach, actually, by strict speaking. If you have domain-specific knowledge, for those of you who do not know, a conjugate prior, there are certain priors that we know are the opposite to each other. They're conjugate. There's only a few. If I remember off the top of my head, I think there's only eight sets in the classical textbooks. But a lot of the time, you won't have that information. If, for example, like the AB one, you knew that the first one was binomial, you can look it up in the table and find your conjugate power. Yeah, which is one of the inverses. You can find that. A lot of the time, though, I do find that as you just get more data, like these things become less and less of a problem. It depends on what the scope is. If you have a very small data set and a lot of domain-specific knowledge, like, for example, perhaps in a pharmaceutical context or a medical statistics context, when you have like quite a small data set, but a lot of domain-specific knowledge. And if you read Cameron Davis's Bahylon's book, which is just an awesome book, he does talk about that picking of priors. So he has an example when they're talking about a financial context of how you could train traders to help you pick a prior, right? So you could like make them do a game. I don't know why you'd do this, but I'm sure someone has. Like, and then gradually get a better, more informative prior. But the whole prior thing is complicated. It's probably more an art than a science at the moment. Although I think there is research on improving our understanding of that in a theoretical context. Is that a good enough answer for you? Anyone else? Again, go on.
Is sample size a bit? Is it a big restriction in Bayesian setup? Because, for example, if you have millions of observations, it's not really a problem for simple frequentist approaches, because efficient algorithms are available. But, for example, if we would like to repeat the analysis with the scene for a couple of millions of observations.
Yeah. So you probably would try to take a better sample of that. Probably would be a better approach than trying to throw all the data at that. But that's just a sampling approach. Yeah. Like Bayesian approach does work very well though if you have unbalanced, so if you have an A/B test with different sample sizes, it works very well, which is actually a big problem in frequentist approach. But yeah, for something like that, I would just sample from it. That's a first approximation, and then maybe see of running it on the full thing. Okay? Anyone else? I can let you all go now. Okay, right, so I think that's it, guys. Thank you very much for listening to me talk this early in the morning. And enjoy the rest of the conference. If you have any questions, I'm here all weekend. You can ask me about them. I'm sure you will, but that's fine. That's what I'm here for. I think that's it.